So in the previous talk, we have seen that we have a scalable algorithm for the purpose of subspace clustering that is being shown to be effective. So in this talk, I'm going to tell you that there is actually an issue with that one. So that in this talk, we are going to take an alternative method so that we can, find a way to mitigate the issue. So recall that in the sparse subspace clustering method, what we do for clustering data point is that we first build a data infinity by running a data self-expression, and then we use the expression coefficient to build the infinity and to cluster data points. So here I'm showing an example of the affinity matrix built from this method, and in which the black means that there is no connection, means 0, and white dots means that there is a connection between the corresponding data points. And it can be clearly seen that there are 3 clusters in this example, and there are actually very few wrong connections, and most of the connections are correct. However, the issue that I mentioned earlier appears here, and that is because of the sparsity of this affinity matrix, and that's going to affect the clustering performance because of the issue of oversegmentation, which says that even for the points that are from the same group, there are very few connections between them, which may cause that the points are not well connected and they oversegmented into different clusters. Okay, so as an alternative, it has been proposed that we can use the L2 regularization instead of the L1 regularization, and as expected, we have now a dense graph, and which solves the connectivity issue of the previous method. However, as we can see from this, the affinity on the right, there are many wrong connections at the off-block diagonal part, and that is an issue and which may cause a degraded clustering accuracy. So if we think about this, actually the properties of these two methods, they actually the properties of these two methods are actually complementary in that one is doing good in connection and one is doing good in getting correct connections. So our idea is that can we combine the advantage of these two methods and come up with a method that does both. And this is the model that we study, that is the elastic net subspace clustering, in which we use both L1 as well as a L2 regularization, and specifically we also use a parameter lambda that trades off the effect between these two terms. Okay, the effect of the lambda parameter is demonstrated using the example in the figure, and on the left-hand side, I'm showing the connection error as a function of lambda. And as we can see, the lowest connection error is achieved when lambda is 1, in which gives the sparse subspace clustering method. And in the figure on the right, we show the connectivity, and this is actually the within-class connectivity. And it can be seen that the highest connectivity is achieved on the other side, where lambda equals 0. So the combination of these two effects gives the clustering accuracy, and as expected, the clustering accuracy is the highest when lambda is in the middle. And this illustrates the effect of tuning this parameter lambda to trade off between these two effects. And up until now, I've demonstrated this trade-off effect using an example, but later on, I'm going to illustrate this trade-off effect analytically using the geometric structure of the solution. And moreover, we are also going to demonstrate that this method is still guaranteed to give correct connections under broad conditions. Okay. Another issue that, if you recall from the previous talk, is that now we have an L1 minimization problem, and we said that it's not efficient to solve, and although there are a lot of current algorithms, they are generally not scalable for large-scale problems. So as another contribution of this work, we derive a scalable algorithm that we do this by exploiting the geometry of the solution, and the method is tested on very large-scale databases and actually on a set of millions data. Okay, now we enter the technical part of the talk, and I will start with an interesting observation on the geometry of the solution of this elastic net problem. Specifically, we identify the concept of so-called oracle point, which is computed from the optimal solution. And we identify this concept because it reveals the structure of the solution in the sense that a point in the dictionary X has non-zero coefficient if and only if the point X is close to the oracle point. And this is illustrated in the figure below, in which I show the oracle point and two right arcs. So the right arcs are what we call the oracle region, in which if a data point in the dictionary lies in this oracle region, then we will have that it has non-zero coefficient, and otherwise it's going to have zero coefficient. Okay, as a first application of this geometric structure, we are enlightened by this to design a fast algorithm. And the idea is that suppose that we know the oracle point delta at this point, and then we immediately tell which entries in the dictionary are going to have non-zero coefficients, right? In this way, we are essentially reducing a large-scale problem to a small-scale problem, because we only need to consider points in the oracle region. So the point here is that the oracle point can only be computed once we have solved the optimization problem. So what we propose to do here is that we iteratively update the oracle region and a support set until convergence, and the procedure is illustrated in this slide. So suppose we are doing this optimization problem, and initially we pick a small support set T, which contains 3 points. Then what we do is to compute the oracle region, which is illustrated on the right, the two right arcs. And notice that this oracle region is computed solely from the support set T, which contains only 3 data points in this case. And then what happens is that there are some points that are inside the oracle region, and there are some points that fall out of the oracle region. And what we do is that we add the first one and remove the second one. And we update the oracle region so that it contains the point that currently lies in the oracle region. Alright? And then we repeat this procedure to update the oracle, to update the support set. And what we show is that the support set T converges to the true support set in a finite number of iterations. Okay. As a second application of the geometric structure of the solution, we explain analytically the trade-off between the correct connection effect as well as the connectivity effect. Again, here in the figure on the right, I'm drawing here actually the subspaces. So the right region is again the oracle region, in which you recall it has the property that if a point lies in the oracle region, then it has non-zero coefficient. So the point here is that we establish the size of the oracle region is controlled by the parameter lambda, in a way that, roughly speaking, if lambda is large, the tuning parameter lambda in the equation, if it is large, then we are going to have smaller oracle region, which means that we are going to have fewer points that are connected, so that we can have better chance of getting only correct connections. And on the other hand, if lambda is small, then we have large oracle region, so that we have more connected points that solves the connectivity issue. And more specifically, we establish the conditions under which the ENIC is guaranteed to give correct connections. Let's start from the condition for SSE, which appeared in the first talk. And the condition for guaranteeing correct connections for SSE for both BP and OMP is listed here, in which the left-hand side is the similarity between the subspaces, and the right-hand side is the distribution of points in the subspace. So it turns out that the condition for elastic net subspace clustering of this talk is slightly different, in the sense that the right-hand side is going to be a function of both r, the in radius, as well as the parameter lambda. And especially if lambda equals 1, then the right-hand side reduces to r, which reduces to condition of the SSE. All right. So I just want to mention here that we have a stronger condition than this one. So this one is actually corollary of a stronger condition, which is available in the paper and in the poster session. Okay, so we tested our method on very large-scale databases. Here on these 4 databases, the COIL, the PI, the MNIST, and the cover type databases. Note that the size of the database ranges from 7,000 to 500,000. And we will be clustering all the available data in this experiment. So first, we illustrate the clustering accuracy of our method ENIC with the previous 2 SSE BP as well as SSE OMP. As we can see, the ENIC achieves the best clustering performance. And this is to be explained by the fact that it offers a trade-off between the effect of correct connection and connectivity. In terms of running time, we also show that our method is scalable in the sense that although the ENIC is not as fast as the OMP method, but the performance is fairly comparable and in the same magnitude. And this is to be explained by the fact that actually we designed the fast algorithm, and this can be seen from the other method SSEBP, which uses the ADMM, and we can see that it is much slower than our ENIC, and it cannot handle the later two data spaces, which are very large scale. So in conclusion, in this work, we studied the elastic night subspace clustering problem. We established that the method has the advantage of giving correct connections and enhanced connectivity, the combination of which gives us better clustering performance. And also we showed that the method can be efficient by using our fast algorithm. I'm just using this slide to summarize also some other methods that we know of that perform subspace clustering and their properties on these three aspects. And as we can see, our method, ENIC, is the only one that does good in all these three aspects. And that's all. Thank you.